Hello, my name is Robert Smith and I'm with New River Community College's Academic Assistants, and today we are looking at heterogeneous equilibria. If you looked at my previous video, you noted that each of the reactions was relatively homogeneous in terms of phases. Now we're looking at instances where the phases are not always match up. So let's look at the first problem. When you write the equilibrium expression for each of the chemical reactions, you're going to get something a little different than last time. So for the first one, we have solid silicon, gaseous oxygen, and they react to make silicon dioxide. So our K value, Kc in this case, would be 1 over the concentration of oxygen. Oxygen is a reactant, so it goes at the bottom. If it was a product, it would go up top. Similarly, you can do our Kp, which would be the same thing, except it would be the pressure of oxygen. The next problem has nickel oxide, so it's nickel 2 oxide, plus hydrogen gas yields solid nickel and water gas. So we have two gases. In this case, we have Kc, and our products are water gas, our products of interest, I should say, and hydrogen gas is a reactant. So that's what our Kc would look like. Similarly, our Kp would have the pressure of water gas over the pressure of hydrogen gas. Last one has, well, we can just do it out. We're looking for gases or aqueous. In this case, we have two gases. So we're not going to worry about water, and we're not going to worry about HNO3, nitric acid. So in this case, Kc product is NO, nitrogen monoxide, over NO2, nitrogen dioxide, cubed. Again, we're raising it to the power of its coefficient. Kp would just be the pressures. So pressure of NO over pressure of NO2 cubed. It's that simple. Now this next problem, and the last problem in this video, is a two-part problem. It gives us a reaction and a temperature at which the reaction occurs, and the partial pressure of each of the species, and in this case they're equal to one another. And we're to calculate both Kp and Kc for the reaction at this temperature. So let's start with Kp, because it's a little easier to do your Kp value when you have nothing but pressures, partial pressures. So in this case, Kp is going to equal products over reactants. But note that the reactant is a solid, so we're not even going to worry about that. So it's just going to be the products multiplied to each other. So in this case, it's going to be the pressure of H2Se times the pressure of ammonia squared. Easy. You can plug that in, and you end up with 0.362 atmospheres cubed, because one of them is squared, and then you're multiplying it by itself again. So it ends up being cubed. And that gives you 0.0474 as your Kp. Now to solve for Kc, recall that Kp is equal to Kc times RT to the delta N. So first we need to calculate what is T in Kelvin. 700 plus 273, so we have 973. And then our delta N is just the sum of the products minus the reactants in gas only. So there's only products in gaseous form, so we just have 3 moles total. There's 2 from the ammonia and 1 from the H2Se. Okay, dihydrogen selenium. So now we're going to take this equation here and we're going to rearrange it so that we're isolating Kc. And all that means is we're going to divide by RT to the delta n power. So Kc is equal to Kp over RT to the delta n. Okay? And then it's just a plug and chug at that point. So we end up with 0.0474 over 0.08206. Again, we're using the gas constant that has the units of liter atmospheres per Kelvin mole times our temperature in Kelvin, which is 973, raised to the delta n, so cube it. Plug that into your calculator and you'll find that Kc is equal to 9.32 times 10 to the minus 8 power. That's all there is to it. That's heterogeneous equilibria. Just make sure that you don't include solids or liquids when you're doing your calculations.